Folks, welcome. You've joined the National Watershed Coalition's webinar for best practices for watershed projects inspection. Paul, Dan, Lisa, I think we're going to get started. We're just a skosh under a couple hundred folks and think that we need to go ahead and start our webinar today. The voice you're listening to is Ray Ledgerwood, your moderator for today's session. This is an informational webinar sponsored by our National Watershed Coalition on best practices for inspection and evaluation techniques of dams for watershed projects. The intent is that principles, concepts, and procedures taught will be readily adaptable for anyone responsible for conducting dam inspections, evaluating their compliance with their current operation and maintenance standards. And also, an objective is to make sure that you'll learn about embankment dams and appurtenances, and the function of typical dam features, common dam failure modes and conditions that lead to those failure modes. Actual dam failure cases will be presented during the course of our event today. Some of the key players I've listed there, Dan, Lisa, Paul, and Ray. The webinar ID, I'll only do this one time, but it's www.joingotowebinar.com. And the webinar ID is 914-879-435. If you're joining us and you have a colleague that needs to get on somehow, you can send those coordinates to them and they should be able to join. If folks are joining just by phone and you can hear our voices, please do go up to the computer because you're going to get so much more out of this presentation and Paul's notes if you do that. All right. Okay. So it's my pleasure to welcome our first speaker. That's Dan Siebert. Dan is our National Watershed Coalition Executive Director. Dan?
Good morning, friends. I trust everyone has their morning beverage of choice and is ready for a couple of hours of excellent information on watershed project inspection. We appreciate you joining us this morning. For those of you that may not be familiar with the NWC, we're a nonprofit organization made up of national, regional, state, and local organizations, associations, and individuals. We have long advocated dealing with natural resource problems and issues using watersheds as the planning and implementation unit for those efforts. My bosses are Lisa Knopf Owen, our current chair, Rex Isom, our immediate past chair. Our vice chair slot is currently open, and our longtime secretary treasurer is Barb Oltgen, who I believe is on the call with us today. And on behalf of those folks, welcome. Again, for those of you who may not be familiar with NWC, we're governed by a steering committee composed of individuals, representatives from organizations and associations. Some of the things we do for both project sponsors and our brothers and sisters at NRCS are conduct workshops and training sessions, and serve as a resource to put sponsors in contact with others who have completed construction or rehab projects. We provide assistance in developing strategies for sources for project funding. As a matter of fact, probably our next webinar will be about project funding. We hold biennial conferences when we are not in the middle of a pandemic. And we develop publications, which you can find on our website, which you may find helpful. They're all sponsor oriented and are downloadable. We do maintain a website and a Facebook page. There you see our website address. There are announcements of workshops, conferences, webinars, and events there. The recording of this webinar will be available there in the near future. There are fact sheets on the Watershed Rehabilitation Program, feature articles on various projects around the country, a number of videos that are downloadable featuring watershed people and watershed work. And a whole series of fact sheets on project funding, operation and maintenance, hazard class changes, dam watch, and other watershed related subjects.
Well, thanks so much, Dan, for getting us off to the right foot here and giving a bit of an update on the National Watershed Coalition structure and our officers. There may even be a vice president out there in our midst of the 200 and some odd folks that have joined us today, huh?
Yeah.
Maybe. Thanks, Dan. Appreciate it. My pleasure to introduce our next speaker, Lisa Knopf-Owen, our chair of the National Watershed Coalition. Lisa?
Good morning, Ray. Good morning, attendees. It's great to see the numbers keep rising on the little ticker over here at 217 currently participating in this webinar. I want to thank you all for taking time out of your day to join us and let you know that this is one in a series of webinars that the National Watershed Coalition has put together. The previous one was on easement basics. I think you can find additional information about that one on our website. It had about 200 attendees for that one a few months ago. And I would encourage you very much to go to the website to gather information. If you like what you're seeing on these webinars and some of the information you've been receiving, that's done by the organization. And the only way that an organization keeps functioning is by membership. And so we're one of the best deals going. I would highly encourage you to become a member of the National Watershed Coalition. As individuals, it's a mere $25. And then there's also organization and association memberships as well. So we have laid out a pretty aggressive plan for this year. One of the biggest jobs of the National Watershed Coalition is to represent the needs and concerns of watershed project sponsors at the national level. And I'm happy to report that that work is continuing with news that was sent out yesterday about the House Ag Appropriations releasing their bill that had $155 million, I believe is the right zeros there. Dan, correct me if I'm wrong, for PL 566 and $12 million for dam rehab. So this is great news and it gives us a great starting point. So I want to encourage you to become involved with the National Watershed Coalition and please visit us on our website and like us on Facebook. Thank
and become
you, Ray.
a member, huh, Lisa? Yeah.
Absolutely. Yes.
Wow. $25 to encourage Congress to put $155 million into PL 566 or $12 million into dam rehabilitation. Sounds like quite a bargain, Lisa.
It is the best bargain going.
Thanks so much. Thanks so much for your opening comments, Lisa. And we've got you on the line for questions later on. Folks, all the lines are muted except for our presenters. The questions we're going to use, and many of you have practiced this already, via the web, use the dashboard on your computer, tap the orange arrow at the top corner of your right-hand top corner of your screen, tap questions, go ahead and type your question in, tap send. We're going to get to as many questions as we can. And you ask about whether the presentation will be recorded. Yes, it will be recorded. And will the slide deck be available? Yes, it will be available too. Feedback's welcome. Kudos, comments, etc. to that address, rayledgerwood@msn.com. I'll be sending you a note after the webinar, and you can send in your informal evaluation and any comments you might have. And to this, I want to make sure that you know that we've asked you to hold the next 120 minutes, till noon Eastern for this webinar, the presentation and questions and answers. And Paul has generously offered to stay on even after that time if we don't get to all the questions, but we're going to get to as many as we can. So our agenda is straightforward. We're just about done with those opening comments, agenda, session, logistics, and purpose. And then we're going to turn it over to Paul Swiger in just a bit here. He is a vice president of the Dams and Hydraulics Section Manager of Annette Fleming. And then we'll turn to questions and responses after about a 90-minute presentation, and it has some closing comments. Now, I did tell you to grab a piece of paper and a pencil, and here it is. You're going to want to write down at least Paul's email address there, and make sure that you know that how to reach Paul if you did have a question or did have a need for those slide deck. Now, the slide deck will probably also go up onto onto our National Watershed Coalition website. So we're going to switch over to Paul here. Paul's going to take it from here on forward. If you do have questions, logistics, questions for Paul, please go ahead and do that. Paul, let's do a mic check, and you're off and running. Thanks, Paul.
Okay, Ray, here's the mic check. Do you hear me loud and clear?
Coming through very well here. Yes, thank you.
And do you also see my screen?
Seeing your screen up fine in the presentation mode.
Wonderful. I'm ready. Can I get going?
Yes, sir.
All right, thank you, Ray. And thank you, Lisa and Dr. Siebert. Well, if you're interested in inspecting and evaluating dams, this is the webinar for you. And I'd like to start by talking about dams that have been in the news recently. Starting with Oroville Dam back in February of 2017. Pretty much everybody in the world knows about Oroville Dam. Not only is it the highest dam in the United States, but what happened to it in February caught a lot of attention. It resulted in almost 190,000 people being evacuated for 3 days. One of the interesting things about this project was that the flows that were in the spillway that caused it, the principal spillway, to suffer this damage that eventually led to the evacuation was only a third of the flows, of the maximum flow that the spillway had experienced in the past. This project had operated successfully for over 50 years. So the question is, what changed? And that goes to asking the question, would inspection and assessment of the spillway have found this problem? And these are the kinds of things that we're trying to prevent. Going to March 2019, looking at Spencer Dam in Nebraska. Now this was a flood and ice event combined, but that caused the failure of this dam. This is an interesting video of a dam in Texas. It was a surveillance video, and it happened to catch the failure, which is rather dramatic, of this dam. Now, just a comment about the videos. Ray and I were practicing some of these, and for some of you that may have a limited bandwidth, the videos may not come through as smoothly as we'd like them to. But this will be recorded, and if you want to watch it later, you'll be able to see these a little bit more smoothly. Now, the last dam failure that you just saw on video, that happened during what we call a sunny day. Sometimes these failures occur during an extreme loading condition like a flood event, but not always. That last one was a beautiful sunny day. Here's another example of a dam that failed during a sunny day event. And this was a piping failure. And we'll be talking about some of these in more detail. And then very recently, here we have Jersey Valley Dam in Wisconsin in 2018. This is a pretty classic looking NRCS type dam. You see the before. And in this case, the failure of the embankment didn't occur. It was a failure of the earth cut grass line spillway that resulted in a complete breach of the dam at the right abutment of this dam. And then the most recent one here, Evansville Dam in Massachusetts, just a few weeks ago, May 19th, 2020. And we caught this dramatic video of this dam failing. So why did these dams fail? And I'm gonna, if you were to ask Yogi Berra, he may say, well, we made too many wrong mistakes. A couple more statistics on dam failures. Since 1980, there have been on average 24 dam failures per year. That's according to the National Performance of Dam Program. They just issued a report back in 2018. Between 1990 and 2000, there were more than 450 dam failures in the United States. So during that 10-year period, more than 450 dams failed. Dams less than 50 feet high caused 88% of the total fatalities between the period of time from 1960 to about 2000. That's from a report that Wayne Graham published. And these last two statistics were kind of surprising to me. I think they may be surprising to you too. Failure of dams with drainage areas less than 2 square miles caused 47% of the fatalities, and failure of dams with drainage areas less than 10 square miles caused 75% of the fatalities. And so that's right in the range of dams I think that most of us on this webinar are normally maintain and inspect. So this is what we're going to cover in the next few minutes. I'd like to start with some dam basics, basically what everybody should know that's involved in inspecting or assessing dams. Kind of gives you a little bit of the history of dam building as well, so you understand how these dams were built. And then really the important question, what can go wrong and what to look for if you're inspecting or assessing dams? What are the most important things? Let's start with the dam basics. Well, here's a map of the United States, and it has a lot of dots on it, and each dot represents a dam that's in the National Inventory of Dams. Now, that's not all the dams in the United States. These are just dams that meet a certain size classification. And there are about 90,000 dams currently in the National Inventory of Dams. If you look at when these dams were built, we have a plot here of the number of dams on the x-axis on the bottom, and then the period of time that they were constructed. And what I'd like to point out here is that the average age of dams in the United States is over 50 years. And that's kind of an important statistic. Most dams, the intended design life is about 50 years. And after that, it doesn't mean that at year 51, the dam is obsolete, but it means that dams really do need to have a thorough evaluation to see if they continue to meet current design standards and that they're safe and ready to continue their service in a safe way. This is another plot that I'm sure many of you have seen. This is focused on NRCS, Natural Resources Conservation Services dams, formerly the Soil Conservation Service, and it shows the dams that were built under different programs. And again, if you take a look at the statistics here, you can see most of the dams now are more than 50 years old. The Natural Resources Conservation Service is responsible for building more dams in the United States than any other agency. The total number of dams is over 27,000 dams in the United States. If you look at dams by type, you can classify most dams by the materials that they were built out of. And you can see one that just stands out here, and that's earth embankment dams. That is the most common type of dam structure that's built. Many other types, there are concrete gravity dams, there are masonry dams, there are arch dams, rubber dams, inflatable dams, steel dams, timber crib dams, rock fill dams. But the ones that we're going to focus on, and I'm sure most of the participants in this webinar are probably involved in inspecting embankment dams, and that's what we're going to focus on. Just one other statistic about dam building, the graph here that it divides dams into two categories, those that are made out of concrete type materials and those that are made out of earth materials or earth embankments. So the red are the earth embankments, the blue are the concrete dams. One of the things that's interesting about this is you can see that concrete dam building was very popular at the very beginning of dam building in the United States, and then it generally has decreased over time. Whereas you look at embankment dams, they really peaked out in the 1960s. At one point, we were building almost over 2,000 dams a year. So why is that? Well, if you look at how dams were built before World War II, you could see a 2 horsepower bulldozer, a 4 horsepower scraper, And then we had a little bit more modern equipment, steam shovels and steam rollers. And then when we need to compact, we used a sheep's foot compaction. Just a little interesting statistics here. This was patented in 1904. The first sheep's foot roller meant to replicate that same compaction from sheep passing over a fill layer. And the first dam to use this was in 1920 to 23, and that was Henshaw Dam. After World War II, things changed quite a bit. Now we no longer have animals helping us to bring in fill and compact it. We are relying on big diesel-powered equipment off road trucks, scrapers, bulldozers, and compactors. And that's one of the main reasons why earth dam building really took off after World War II. It became a lot more economical and efficient to build these types of dams. Now, this is what we're going to focus on. This type of dam and this type of layout is pretty classic for the Natural Resources Conservation Service, where you have an earth embankment, a principal spillway or riser structure. You have an impact basin or some type of energy dissipation at the outlet, and an auxiliary spillway, normally an earth cut grass line type spillway. So that's what we're going to focus on. And we're going to start and take a few minutes to look at each one of these structures and talk about their purpose and importance, starting with the principal spillway and the riser structure. This is the most modern classic layout right now for an NRCS type riser structure. It's a very important structure, and it serves a lot of purposes. One of the main purposes is to control the normal pool. So the top of the structure acts as a trash rack, and it's equipped with, we'll look at a cutaway here, with two weirs. The walls on the sides act as weirs. So as the reservoir increases because of a rainfall event, water will fall down over the weirs, drop down to the bottom, and then be conveyed through a conduit. Now, this riser structure has other features as well. It has an intermediate gate to help maintain the pool level and maybe to do some maintenance. It has a water supply intake that's kind of unique to this one. Not all riser structures have this. And then, very important, a low-level drain to be able to drain the reservoir in the case of an emergency or because of maintenance. This is probably what you'll normally see if you go out to a dam and you look at the riser structure. You'll probably only see the upper part, which consists of the bonnet, and it has trash racks, and that's the part that is above the normal pool. Now you're probably saying that's maybe that's not what my dam looks like. I put in some examples. Early on, the NRCS was doing a lot of experimentation and coming up with different designs. Now the one that you see here, that is now the classic design. It's kind of the perfect riser structure. But there are other configurations as well. Here's an example of one in West Virginia and another one, and you can see they're all variations of the same thing. They just have slightly different configurations, sometimes inlets at different levels, but they are all serving the same primary purpose, to act as the principal spillway. And for flood control projects, you sometimes have multiple inlets to address different flood control needs. But I just want to show that there are different layouts and different configurations of the same type of riser structure. They're not always in the reservoir. Sometimes the top of the riser structure is incorporated into the embankment with a conduit extending into the reservoir, like you see here. Sometimes they're made of concrete. And this is, I tried to show as many examples as possible. This is the largest concrete riser structure that I've come across so far. This one's in Tyler Dam, Massachusetts. And it is so large, I think you could probably play tennis on top of this riser structure. all the way down to the simpler type. And this is simply a corrugated metal pipe riser structure with an anti-vortex device on the top. And it's serving the same purpose as the other examples of riser structures that I showed. And here's a video of one that is, you can see what's going on in the top. So if you were to try to look through the top, you can see the two walls on the left and the right. And so the reservoir, as it comes up, it flows over the top of the wall, and then it drops down. You can see here, this one's flowing at a pretty decent capacity, and it drops down to the bottom of the structure, and then the water is conveyed through the conduit, through the dam, to the downstream structure. So that gets us to the outlet. And connected to the riser structure is a conduit, and the conduit is normally connected to a impact basin, or it extends into a plunge pool. So this is the classic layout of an impact basin for an NRCS type dam. And this is a cutaway, so you can see as the flow comes out, it has very high velocity, high energy through the conduit. And this impact basin is designed to dissipate the energy before the flow is released back into the stream at the toe of the dam, and to prevent erosion of that area. This video is taken during a flood event. So if you were to go to the top of the dam and look at the reservoir, in this particular case, you wouldn't even see the riser structure because it's under several feet of water. And that's an indication that the conduit is flowing at its maximum capacity. So it's flowing full, and you can see the good job that the impact basin is doing. Now, here we're just looking at the outlet, but here's a video that shows really what's going on. So this one doesn't have a covering on it, but you can see that high velocity flow impacting the wall in the impact basin, and highly turbulent, and dissipating the energy so that the flow that's leaving is a lower velocity and doesn't cause erosion of the outlet. In other cases, an impact basin may not be needed. For example, if at the toe of the dam there's good bedrock or a nice deep plunge pool, you can simply have the outlet of the pipe discharging into the plunge pool like you see here. Then we move on to the auxiliary spillway. So the purpose of the principal spillway is to pass flow pretty much all the time. So all the base flow and the normal flow that enters the reservoir goes through the principal spillway. But you reach a point where the capacity of that conduit and the riser structure is limited. And most of the auxiliary spillways are designed to be activated for a 100-year event. So the floods up to the 100-year event, all that water is passed through the principal spillway, and then flows that exceed the 100-year event will pass through an auxiliary spillway to prevent overtopping of the dam. Now, there are other criteria. Sometimes it's activated more frequently, sometimes less frequently, but most auxiliary spillways are set for a 100-year flood event. Now, when you look at a classic grass-lined earth-cut auxiliary spillway like the one here, you'll have an entrance condition, and that is normally a 2% upgrade until you reach the level control section that's normally in alignment with the dam, the crest of the dam. So this rectangle here that you see in yellow, that's a level section, and that establishes the control of the spillway. So flows approaching the control section are subcritical. As they pass over the control section, which is the highest point in the spillway, the flow will accelerate, it becomes supercritical, and then it discharges down the outlet channel of the spillway, which is normally also a 2% grade. One of the design requirements for most of these spillways is that the exit channel from the control section going downstream has to maintain a straight alignment, at least to the point where it passes beyond the toe of the dam. After that point, the flow is then allowed to return back, and you're allowed to put a curve in the channel. But that section from the control section to the toe of the dam needs to be straight. And we'll talk more about the performance of these spillways in a little bit and what to look for. Now, in some cases, really the ideal situation is if you can take the auxiliary spillway and provide a distance or a separation zone between the spillway and the embankment. That's ideal. But the topography of many dam sites just doesn't permit that. And in some cases, the spillway is located immediately adjacent to the embankment, like what you see here. So here we have a grassline spillway, and you can see the embankment in the background. And in order to prevent the spillway flows from going down the groin of the dam, you'll often have a spillway training dike. So that's a very important feature of an auxiliary spillway, because it contains the flow within the spillway and allows it to discharge safely away from the dam embankment. Here's a video of a very large grass-lined earth-cut spillway. This one is Beach Dam in Tennessee. And this is a very wide spillway. Now, with a lot of the auxiliary spillways, when they start to get this width, you'll sometimes see a splitter dike within the spillway to divide the flow. This spillway does not have a splitter dike. What would this look like during a flood event greater than the 100-year? Well, this particular spillway did flow, and we happen to have some really good photos of what that would look like. So this is a very well-maintained spillway. You can tell that the grass is well-maintained, it's mowed, and when this spillway was activated, you can see how well it performed. The water is nice and uniform, and at this point, the flow is moving supercritical, so it's moving pretty fast, and the spillway is performing very well, just as it was intended to. So that's an event that exceeded the 100-year flood event. Now let's look at the embankment. The first dams that were built before there was a lot of engineering that was put into them were very simple, homogeneous earth embankment dams. And here is a cross-section through what I would call a typical homogeneous dam. Most of the dams built before the 1940s, many of them were this simple. And if you think about what kind of seepage could we have through a structure like this, we can have seepage through the embankment, and that seepage, just to establish some important nomenclature here, as the water flows through from the normal pool through the embankment, it will saturate the embankment and will have what's called a phreatic surface. So if you were to put instrumentation in the embankment, anything below this dashed line would be saturated. So that would be like a column of water. Above that, it would be dry. And in this case, in this cross section, you can see the flow going through the embankment from the reservoir level, from the high to the low. And if we were inspecting this homogeneous earth embankment the way it is now, we'd probably see the downstream slope wet from this point down. Now, that's not the only place that water can flow. Water can also flow through the overburden material and then through the bedrock. So the overburden material is a layer of material that's sometimes weathered bedrock, and sometimes it's alluvium, or it's deposited by water flowing down the valley, and it's sands and gravels and things like that, sometimes clays and silts. But those are the three flow paths for an embankment. This is a video that shows as the reservoir comes up, and here we have a nice homogeneous earth embankment, and you can see the dark zone. This is the wetting front. So as the reservoir comes up, the embankment will become saturated, and that changes the state of the dam a little bit. Now, for some dams that are flood control dams, they could be dry most of the time, and only during flood events will the reservoir fill. For other dams that might be multi-purpose, you might have a normal pool for recreation or for water supply, and also a flood component. So there might be a part of the dam that is saturated. Now this is the same video, but it shows later on, you can see the dark zone. Now we have a completely saturated embankment. In fact, we have a wet zone with water seeping out of the downstream slope, and you can see that it affected the structural integrity of the embankment. As that embankment, this particular homogeneous earth embankment, became saturated, the strength of the embankment changed, and we had a pretty classic slope failure there. That was not a piping failure, that was a slope failure because of the saturated embankment. So as we learned more and more about the performance of dams, we realized that this is not the kind of condition we want in our embankment dam. When we inspect dams, we do not want to find any seepage or a saturated condition on the downstream slope of the dam, because that can lead to sliding problems as well as erosion problems. So engineers started modifying dams, and this is kind of going through the evolution of embankment dam building. And it's important to know, especially if you're assessing your dam or inspecting your dam, to have a general understanding of how your dam was built. So your dam may have a blanket drain if it's kind of the next generation beyond homogeneous embankment dam. And the purpose of this dam, this blanket drain, is to intercept seepage and then convey that seepage through the embankment in a controlled way. That also reduces the phreatic surface and will dry the downstream slope. So it pulls that phreatic surface down. The hydraulic gradient is going from the reservoir through the embankment into the blanket drain. But you still can have seepage through the overburden and through the bedrock, but this is an improvement. Something that can happen is that this overburden material may not be homogeneous itself. You may have on the surface a clay layer, for example, and then below that you could have zones of sand and gravel. And that can make conditions complicated for a dam. As you can imagine, you can get more seepage through the sand and gravel than you would through the clay layer. And that can cause an artesian condition to develop as well. For example, if you had a piezometer, I'll just go back here, if you were to put an instrument at the toe of the dam and you had a condition like this, you could have a pressure condition below the toe of the dam that is much higher than the ground surface. So this would absolutely be a concern, because what this could do is lead to seepage at the toe of the dam, or boils where water pressure is greater at the toe and it wants to seep up vertically through the sandy gravel layer. And if it can penetrate that confined layer, then you could have a real problem. So what engineers will do, if you have a case like this, one of the solutions is to put in relief wells, and that will intercept that seepage and collect it and safely discharge it away from the dam, and not so that you don't have these boils and seepage uncontrolled at the surface. And so if you have a dam with relief wells, it may look something like this. So here we're at the toe of a dam, and you can see all these white pipes. Those are the tops of the relief wells, and then they go down vertically in, and they penetrate through the confining layer into the sandy gravel layer. And then if there is artesian pressure, it will come up, it will be collected, and then it will be safely discharged at the toe of the dam. Then as dam building continued on, engineers tried different things. They tried, in some cases, to put an impervious barrier in the core of the dam. In this case, they were using a concrete wall, which was pretty common up till about 1930. So here's a cross-section of an embankment dam with a concrete core wall. And that's what it looks like during construction. You can see they were building the concrete wall concurrent with the placement of the embankment fill. Then later on, we started getting, especially with being able to place earth fill with modern equipment, started looking at zoning the embankment, putting a clay type or a more impervious zone material in the core of the dam, and then the more porous material in the shell of the dam, and excavating down to bedrock and intercepting that zone through the overburden to eliminate seepage through the overburden. And then to prevent the seepage through the foundation, we began to drill and inject a grout into the foundation to seal up all the cracks and prevent seepage through the foundation. So now we're finding ways to control seepage through the dam. Now this modification resulted in a higher hydraulic gradient right at the interface where the clay core met the shell material. And as we're going to look at in a little bit, there things can happen to the core of the dam. There can be cracking and settling and things like that. And if you get concentrated seepage through here, it's possible for that seepage to pick up particles of the clay material and then discharge that, and then you can have a failure of the dam just by erosion. So the next step was to put in a chimney drain and a blanket drain. And this chimney drain, the purpose of it was to intercept the seepage, to filter it so that if there was any fine material from the core of the dam, that would be filtered and only clean seepage would be discharged through the dam. So the concept here is to have controlled seepage through the dam. It's filtered and it's controlled. And if you look at what this looks like, a typical chimney drain with a blanket drain will have a concrete washed sand. That's the most common type of filter material. That's the fine aggregate. And then near the outlet, we'll often have a number 8 stone or a pea gravel. And then inside of that, we'll have a perforated pipe. A lot of the earlier dams use corrugated metal with perforations. The more modern dams are using plastic pipes like HDPE or PVC because they last a lot longer. So now we're looking at Fontenelle Dam. This is a dam that was built with that exact same detail that we saw. It had a clay core, it had a chimney drain, it had a blanket drain. And as these photos show, we still have a problem. So we're missing a detail. There's still something missing from our design. So let's take a look at this. And can you tell, what did we learn from Fontenelle Dam that is missing in this detail? There's one last piece, and I'll give you a clue. If you take a look at this zone, this is where the problem developed at Fontenelle Dam. And what was missing was we still had, although we have controlled seepage through the clay core and through the upper part of the dam, we still have uncontrolled seepage, or the potential for uncontrolled seepage, through the overburden material. So the last step in the evolution of modern dam building was to make sure that we have a filtered seepage system that starts from the bedrock and goes all the way up to the top of the dam. So that's a modern dam. Now some dams, especially dams that have been modified, will often have a berm, a toe berm. And that's the most common reason for the berm, is to improve the dam for seismic stability. So if you're in California or Illinois or in an area where there's high seismic activity, that's a common feature. And then protecting the upstream slope of the dam with riprap. So those are common features for a modern embankment dam. So here's a video that shows the layout of a modern NRCS type dam. We see the auxiliary spillway, and this one is an earth cut spillway, and it's discharging away from the dam, which is ideal. You see the contact of the embankment with the natural terrain is armored. That's the groin of the dam, and that's a place where runoff will concentrate sometimes. We have the impact basin here at the toe of the dam. We're going to go up over the embankment and look at, I can see the video is running a little bit slow here, so I think I might end up skipping over it. Oh, here we go. It's moving again. In the downstream slope, we have some instrumentation for high hazard dams. That's a common feature so that we can monitor the phreatic surface within the embankment. This particular dam has a normal pool. You can see the riser structure. There's a lot going on here. There's a staff gauge. There's an access ladder. This one would be accessible by boat as you go out. It has the water supply intake mounted to the side. Very important, the low level drain. All dams should have a low level drain to drain the reservoir. You can see the trash racks built into the bonnet. And now we're cutting away from the dam and we're taking a cross section. And you can see how the embankment is zoned. You have the clay core, a concrete plinth, the very important chimney drain and blanket drain to control any seepage through the embankment. And then you can see the conduit, that's the drain conduit that's used to collect the seepage and discharge it through the walls of the impact basin. And this particular one has a grouted foundation as well as consolidation grouting at the contact between the clay core and the bedrock. So a very well-designed modern embankment dam. So that gets us through the dam basics. It kind of gives us a foundation to build on. Now let's answer the question, what can go wrong and what should we look for? So this is getting more into the inspection and assessment of dams. And we're going to pretty much focus on earth embankment dams, the classic NRCS layout with a riser structure, the outlet works, the conduit, the embankment, and the auxiliary spillway. So here we're going to look at the common causes of dam incidents and failures. In the column, we're going to have fundamental causes, and then we're going to put the percentage. So I'd like you just to think for a minute. If you were to guess at the most common reasons why these types of dams have incidents or failures, what would you put in that list and what percentage? Now, there are different databases that have slightly different numbers, but they seem to always come out to be about the same percentage and the same ranking. And this is important because you should be spending, if you're assessing a dam or inspecting a dam, you should be thinking about the things that matter the most. So here we go. If you look at this, you will see that 75% of the dam failures are because of three things. The number one has to do with seepage and piping. And piping is just one kind of internal erosion. You probably should say seepage and internal erosion. Then there's overtopping, which is really a failure mode that's specifically related to earth embankment dams because they are erodible. If it was a concrete dam, overtopping failure is very uncommon because concrete can withstand overtopping. And then spillway, erosion, and breaching. So those are the three most common failure modes for I would say the watershed coalition type dams. There are others, deformation, sliding, gate failures, faulty construction, earthquake instability, and even sabotage, but they are much less frequent. So let's start with what's most important. And I'm going to start with overtopping. More recently, we've had more failures because of overtopping than any other reason. And what does it look like? Well, when you get to this mode, when you get to this point, it's going to be a bad day. You can see water just beginning to flow over the crest of this embankment. And as it gets worse, it begins to concentrate. And if the crest of the embankment isn't level, it will concentrate where the embankment is at its lowest. Oftentimes, these embankment dams are built with a camber to, in other words, the main section of the dam is overplaced, it's placed higher than the rest because to account for any settlement that might occur. But most of the dams are so well built that they don't settle very much, and then the concentration will be at the groin or at the abutments of the dam. And then as they get overtopped, the flow is the flow velocity down the downstream slope accelerates, and it will erode the embankment and wear out the grass lining if there is one, and then the dam will breach. So that's pretty classic overtopping failure progression. I just pulled a couple of statistics out. If you remember what happened in October 2015, when Hurricane Jacqueline hit the East Coast, and it really focused on South Carolina. And there was one part of South Carolina that the rainfall really stalled. And you can see where all of these red circles are with the black dots. Those are all locations where dams were overtopped and failed. And during just that one event at this location, 52 dams failed because of overtopping. And here's one of them. I remember going down and helping out the state during this emergency and looking at these dams and inspecting them. But 52 dams just in one event alone. And if you take a look at what happened, you can see how the rainfall came in. And in this light kind of gray area here, there was more than 2 feet of rainfall that fell in that area. And that was where these 52 dams were overtopped. They didn't have sufficient spillway capacity, and they all failed. So let's talk about that a little bit. If you look at this, this is a world record in the United States, and it happened in Holt, Missouri, back in 1953. And they had an actual rain gauge, and this gauge measured 12 inches of rainfall in 42 minutes. Not only is that a record in the United States, but it is, I believe it's a world record. That's the most rainfall in that period of time, 12 inches in 42 minutes. Now, if you look at what happened when Harvey hit Texas back in 2017, during that event, there was 65 inches of rain that fell during a 3-day period. Now, I want to ask you a question. What would you rather have for your dam? Would you rather have 65 inches in, sorry, it's 7 days, not 3 days, 65 inches in 7 days or 12 inches in 42 minutes? I know when we are looking at rehabilitating dams, we often will focus on the 24-hour rainfall. And for many parts of the United States, it's about 36 inches in 24 hours. And a lot of people look at that and say, well, that's impossible. How can you get that much rain in a short period of time? Well, it can happen, but it is unlikely or less likely, because after all, it is called the probable maximum storm. I wonder if we shouldn't have called it the probable or the improbable maximum storm, because it is on the outer limit of what can happen. But going back to this, what would you rather have, 65 inches in 7 days or 12 inches in 42 minutes? Well, if I state this a little bit differently, I think it might help you with your answer. 65 inches in 7 days, if that rainfall were to fall uniformly or at a constant rate, it would be less than 1 inch per hour, versus 12 inches in 42 minutes, that's more than 17 inches per hour. And for dams with smaller drainage areas, and most of the NRCS dams are between 2 to 10 square miles, some of them go up to about 20 square miles, but we're looking at a time of concentration where when a drop of rainfall hits the farthest part of the watershed to the time it takes for that drop of water to reach the reservoir, we're often looking at a time of concentration of about an hour, maybe 2 hours. So it's really not the 65 inches in 7 days that matters. It's the very intense rainfall that will determine how much water, the rate coming in, and the spillway capacity needed. So I'd rather have the 65 inches in 7 days rather than the 12 inches in 42 minutes for most dams. If the volume of water was really important because of a very large drainage area with a very large storage, then the 65 inches may be more important. So what do you look for in a dam if you're concerned about overtopping? Well, spillway capacity, obviously. You want to make sure you have enough spillway capacity, and you'd be concerned maybe of something like hazard creep. Maybe you have a low hazard dam or significant hazard dam, and now there's development downstream. And because of that, the spillway needs to be designed for the probable maximum flood, and it wasn't, because it never was intended to be that class of a dam. So that's the first thing you would look at. But if you're inspecting the dam, now you're looking at the crest of the dam and you're saying, is there any low spots in the dam that could result in overtopping? So that'd be one thing to look at. Another thing is, how well maintained is the crest of the dam? And I'm looking at this one, and I'm pretty sure that whoever was building this dam or maintaining this dam deliberately planted these trees. It looks like they're pretty evenly spaced, and they're just on the outer edges and not on the downstream slope. So that's a real no-no. There should be no woody vegetation on the dam, especially at the crest of the dam. So if I was inspecting this, this would be a deficiency. Why? Well, these trees, as they get older and older, eventually they are going to die. In most trees, when they die, they get blown over like this. And if it gets blown over and it has a fairly substantial root system, you're losing your freeboard, and you could actually breach the dam. And that's exactly what happened at this dam. There was a tree right where this void is, and you can tell, obviously not a very well maintained dam, but that tree got blown over. It took the root system with it, and you can see the root system of the next tree that's built on the dam, and you can see how invasive that was in the embankment. Another reason why a dam can be overtopped is because the spillways become clogged. Well, here we have the principal spillway, and it's equipped with a trash rack, which is really important, because the last thing you would want is for the conduit to be clogged. So the trash rack is doing its job here, but this particular trash rack may not be adequate. It could, because of the debris, could clog it. Now, there still is the backup, which is the auxiliary spillway, but both spillways are supposed to be doing their original function. Now, here we have a larger riser structure with the trash rack. Now, the trash rack's doing its job. It's preventing the debris from accumulating. But obviously, if we were inspecting this dam, this would be a maintenance issue. We want to make sure that the principal spillway continue to function, so that we do have the flood control storage in place, and the project can do its job. So this would be a deficiency. Sometimes you get some really strange things that can happen and affect the capacity of the spillways. This is one problem that was sent by someone that was maintaining an NRCS dam in Fayetteville, Arkansas. And I remember he sent me this, Paul, have you ever seen this before? We're having a problem with filamentous algae. So there was a blanket of algae on the reservoir, and it basically floated over the riser structure and clogged it. This is another unusual condition, and it's really the poster child for why we need to inspect the conduits in dam. Now, this conduit was large enough that it could be inspected by a manned inspection. It was a 5 by 5 foot opening, and we could walk through the conduit. And as we approached the riser structure, this is what we found. And it turned out that the beavers were very busy. They were cutting trees down on the toe of the dam and bringing in the branches one by one, and the entire riser structure here was being filled with woody debris. So if nobody took the time to inspect this, eventually you wouldn't detect it from the outside, except all of a sudden the reservoir would start to rise above the principal spillway inlet, because the inside would have been completely clogged. And this is another unusual case. And I remember when Mark sent me this picture, he said, Paul, do you know what's going on? I went out to my dam one day, and all of a sudden the intake pipe that went to the riser structure was in this configuration. And my theory is, again, this is probably related to beaver activity, where the beavers got busy and they clogged the entrance to the riser structure, and that dewatered the pipe that was submerged. And because it was a corrugated metal pipe, it floated. It didn't have enough weight to keep it down, and it just floated up above the reservoir. So just another thing that to look for. And then moving on, not just to the principal spillways, and this was a case where in Wisconsin, where there was a flood and the farmer had placed all of his hay bales along the shoreline. And then the flood carried all of these hay bales, floated them into the reservoir. And the first thing they did was they plugged the principal spillway riser. You can't even see it. It's completely covered with hay bales. And then the same thing happened at that project with the auxiliary spillway. It clogged part of the auxiliary spillway and forced the water to one side and caused it to erode. Here's another example of the hay bales, only these are wrapped with the white plastic, so they look like marshmallows. And these are really prone to floating, and you can see how they obstructed this spillway, especially because it had a bridge across the top, which caused them all to accumulate. And just like with principal spillways, auxiliary spillways can be obstructed by beaver activity as well. Here's a beaver dam being built across the entrance of the spillway. Sometimes what you'll see when you're out inspecting it is that these are great places to store materials and things like that. In this case, we're standing at the crest of the spillway, we're looking downstream, and you can see it's a place where debris is being stockpiled. So what that can do is limit the spillway capacity, because you're essentially filling in the spillway. And the more you fill it in, the less discharge capacity that it will have. So these spillways need to be maintained without any obstructions. And sometimes the obstructions are deliberate, but they're unintended. This is a case where we were inspecting this spillway, and the farmer wanted to get his equipment across the top of the dam so that he could mow his fields on the far side of the dam. But the slope on the side, the way the dam was built, was just too steep. It was a 3 horizontal to 1 vertical, and he couldn't get his tractor and equipment up and over. So he solved that problem by building a ramp. So now that he could drive up and over, not realizing that this is the crest of the spillway. That's the level control section. And by placing a ramp there, he was filling in the spillway and had reduced the capacity of the spillway by approximately 30% by doing this. And if you ever had the design storm, you wouldn't have that spillway capacity and you could overtop the dam. This has been observed several times at dams, so something to look for and to be aware of it. This concept of hazard creep, where there's more and more development closer to the dam. This is one where here the house is actually built almost on the dam, and here we have the auxiliary spillway. It's we have the driveway and some materials being stored, and there's a shed down here. So things that can happen over time. Something else that's a little bit more subtle and not so obvious is at the entrance of the spillway. We have the approach channel that's connected to the reservoir. So as the reservoir comes up, flow goes up the 2% grade to the control section and then through the spillway. And what can happen is along that shoreline, originally when the dam was built, there was no woody vegetation at all. And you can see the before pictures. This is probably after about 20 years after the dam was built. That part of the entrance of the spillway was not being maintained, and large trees were permitted to grow there. Well, eventually that could become the new control for the spillway and obstruct the flow through the spillway. I've even seen cases where these auxiliary spillways, it's almost like they get forgotten, and the people responsible for maintaining the dam don't even realize that it is an auxiliary spillway. So if it stops being maintained, the brush will grow into it, and then we start having trees. We actually inspected one where we found this sign that said, "Keep off future forest," and not realizing that this was a very important feature of the dam. And the worst one I think I've ever saw was in South Carolina. This is those 55 dams that failed. This was right in that geographic area. And they had engineers go out and babysit all these dams during the event. And one engineer went out to this site and he found this sign. It said, "For sale, exclusive lake lot, 4.25 acres," not realizing that that was the auxiliary spillway. So in this case, the owner of the dam didn't realize that he was about to sell this lot, which happened to be the auxiliary spillway. And fortunately, that was identified, and they didn't sell their auxiliary spillway as a vacant lot. But that it just shows you what can happen over time if one generation doesn't pass on the information to the next, and these dams are not assessed and inspected, evaluated. So that's talking about overtopping. So it's not just inadequate spillway capacity, but there are a number of maintenance issues that go into that as well. Now let's talk about seepage and piping. And this is a little more complicated. And that's why we took a little bit of time up front and looked at the evolution of an earth embankment dam. By looking at this one, you can see this is a very serious condition. And what you see in this picture is uncontrolled seepage. You know it's uncontrolled because of where it's coming from the dam, what it's doing to the dam, and also by the color of the seepage. It's brown, so it's picking up embankment material, it's eroding it, and it's just a matter of time, and this dam is going to fail. So it's important to know how the dam was built. Now in this slide, this is really unusual that you would see seepage coming out of the downstream slope like this. It also shows why it's so important to maintain the downstream slope well mowed so that you could see something like this before it becomes serious. But the most common location for seepage through an earth embankment dam is where there's a penetration through the dam. And that is normally where we have a conduit. So you have our riser structure, that's our principal spillway. There's a conduit connected to it, and that goes through the dam. Now, if you look at this one, it has all kinds of defensive measures. It has these anti-seep collars, it has a concrete cradle, it has a good pre-stressed concrete cylinder pipe with watertight joints, yet we still see that this is a problem. And I could show you probably, I've got about 100 pictures of dams, different dams that have failed. And what's common about all of them is that they failed where there's a penetration through the embankment. So if you're inspecting a dam or assessing it, this is probably the place you need to slow down and really look. Is there any seepage coming out from around the exterior of the conduit? Any depressions, sinkholes, or anything like that? And the reason why there are a couple of reasons why you can get seepage along a conduit. And the most common reason, and I'll show you a schematic here in just a bit. So here is a conduit that was placed through the embankment, so that's the penetration. And then they place the embankment below, on the sides, and above. And we also have the loading that's shown by the size of the arrows. So we have more load at the maximum height of the dam than we do at the ends. So if we were to exaggerate what could happen here, you can see that the conduit will deflect and the joints can open up. So that's one of the nice benefits of using pre-stressed concrete cylinder pipe with long joints. They can generally accommodate this. But if you get seepage into the joints, that would be a real concern, because that could be where you have the shortest flow path and soil coming in. And if you were to inspect the dam and see the soil deposits in the conduit, that would be a clear indication that you have erosion going through of the embankment material, short-circuiting and going through the joint into the conduit. Most times you will not see this evidence because it's being flushed out as water goes through the conduit. Now, this is an extreme case where we have differential settlement at a conduit joint. And the location where this is most likely to occur is either at an anti-seep collar or at the connection of the conduit with the riser structure. Most riser structures, the foundation is deeper than it is on the conduit, and the conduit could be placed on compressible material. So as the embankment settles, it can push the conduit and it can actually shear from the riser structure, which is sometimes built on bedrock. So it really can't yield at all, and you'll get a concentration there. And the same thing can happen with an anti-seep collar because it's more rigid at that location and less compressible. With some conduits like corrugated metal, they can deteriorate with time, and you can see this one here clearly failing because either of it's just losing its strength over time, or it wasn't designed for this loading condition with this much embankment material above it. But most likely what you will have, especially with the corrugated metal pipes, is that they can deteriorate and corrode over time. And if you get an opening in a conduit, whether it's an open joint or deterioration of the conduit, you can start with a little bit of seepage going through and very high hydraulic gradient. And then as that seepage, if it has direct contact with the embankment material, you can have embankment material flowing into the joint and out of the pipe. And as that progresses, eventually you'll have a direct connection with the reservoir, and then you'll have a failure through the conduit and loss of the reservoir. And that's exactly what happened at this dam in North Dakota. So here's our inlet of the principal spillway, and the dam owner went out one day and he saw a great big sinkhole at the downstream face of the riser structure. So his solution was to go in and place some larger material, and did that, and then came out a little later and it was bigger because he really didn't address the fundamental problem that was going on until the dam breached right through that location. And the root cause of this failure was the deteriorated conduit. Corrugated metal pipe has a service life of anywhere from about 7 years up to probably around 30 or 40, maybe a little longer in some conditions. But of all the pipes, a corrugated metal pipe has the lowest service life. And in this case, when they pulled out the pipe, you could see the whole bottom was rusted through on there. If you're inspecting a dam, like I said, you spend your time, you try to estimate where that penetration is through the dam, and not only looking at seepage at the outlet, but this is on the downstream slope, and you can see here we have a sinkhole in the downstream slope, and that was a place where that pipe had a defect, and seepage was going in and above the defect and showing up there. So it's really important to inspect these conduits. And the best way to inspect them is with some kind of remotely operated vehicle. You can see this gentleman is inserting one here. That vehicle is connected with a cable to the surface of the dam. Here we have a mobile unit, and there's an office built into the back of it so that the operator can create a video of the inspection. Here's just a short video clip of what that might look like. So here we have the ROV is driving up the dam. He knows this is at station 341, so he's 343 feet up the conduit, and he's got a pan and tilt and zoom camera. So he's looking at every joint and getting a measurement and an inspection, so he knows how watertight each joint is. He's able to see if there's a joint opening, if there's a defect, a crack, any seepage or leakage. And in this particular inspection, as the video was made, as he went near the core of the dam, the conduit actually did have a sag in it, and that's why there was water, as well as a little bit of a leak in the gate. So those kinds of inspections can be done even under those conditions. Just a matter of adjusting the wheel height or the wheels on the ROV. Everything we said about the conduits is also true about the drains as well. Those are important features in the dam, and they need to be inspected and maintained as well. Some of the problems that you might encounter with a drain at the toe of the dam that you wouldn't normally encounter with outlet works, though, are precipitates. So that as the groundwater or the seepage is collected and filtered, when it finds its way into the drain pipe, which is normally perforated, it responds to the oxygen and you can get a precipitate. And in some cases, that precipitate can clog the pipe. So these drain pipes, the modern on a modern dam, you will have a clean out at the upstream end of the pipe, so you could flush it out periodically as well as do a camera inspection. Unfortunately, most of the dams that were built with this type of drain pipe do not have that feature. And if a dam is being rehabilitated, that's something that's often addressed at that point as part of the rehabilitation. But many dams are not. So when you're inspecting a dam and it has this feature, some of the things you may see are little sinkholes along the toe of the dam where the drains have collapsed, which is an indication that they may not be functional anymore either, because they could be obstructed. As you're inspecting an embankment dam, something else to be aware of, and this is something that an engineer whose name is Arthur Casagrande, his contribution to this field was, if I was to summarize what he would say, is pretty much assume that if you're inspecting an embankment dam, that there's a crack in the dam, because it's all the embankment materials pretty much are susceptible, if they're well compacted, to cracking. And the cracking can be either longitudinal along the length of the dam, like you see here, or transverse. So this is a fairly large longitudinal crack. And this one's in the crest of the dam, so it's something to look for. Here we have a couple of cracks. Now, why would you get a crack like this in a dam? It could be for a couple of reasons. This particular crack was related to a sudden drawdown, so that the reservoir was up high for a number of days. It saturated the upstream slope, and then it was drained very quickly, so that the embankment didn't have a chance to, it was saturated, it didn't drain, and that additional water load caused it to crack. Now, then you can also have transverse cracking. Those are more serious because they go upstream to downstream and they can create a seepage path. And there are different reasons why. And I just explain a couple of things. One of the reasons why we have so many problems with seepage at the conduit, and that's often the place where the dam will fail. Even if you have anti-seep collars and a concrete cradle, you can get a failure there, because at that location, that's a hard spot in the embankment. And to the left and to the right of these anti-seep collars and the conduit, the soil is compressible. But right at the conduit, it is not. That's a rigid structure. So that creates stresses immediately above the conduit, and that can cause these transverse cracks. And these cracks may not show up on the crest of the dam. They may not even be visible. But that's one of the primary reasons why we have so many failures of embankments, is that they don't have a defensive measure for this. The other reason for transverse cracks is you could have anomalies or changes in the foundation and differential settlement, and that will cause stresses in the soil and cause the cracks to develop. Here's a classic example where in the foundation you may have a bedrock that comes up and then dips down. So the embankment is more compressible on the left and right sides of this, and then you'll get stress cracks as the embankment tries to bend over this bedrock feature. Here's some research that was done by the NRCS, where they went in and excavated along the longitudinal length, so the left to right of the dam. And this is a transverse crack, just to see how deep some of these cracks can go. And in this case, it looks like it went down almost the full height of the dam. Another thing to look for when inspecting the embankment and looking at seepage type failure modes is sometimes you get so focused on the embankment that you don't look at what's going on in the reservoir. And right along the shoreline is a real important place to take your time and to observe and actually look into the reservoir to see if there's any evidence of seepage. So here, for example, we see a little a vortex, and there's a sinkhole developing right below the water line and the upstream side of the dam. This one is a little bit more obvious, and it could be related to a sinkhole developing in the dam, but it could also be the riser structure that's submerged, and that is a vortex related to that. So it's important to know why it's the location and what's going on. Now, if you see something like this, now we're into an emergency mode. This is really getting serious, and we have a sinkhole and then uncontrolled seepage through the embankment. Another reason for seepage, believe it or not, is animal burrows, especially as you approach the crest of the dam and the section of the dam becomes more and more narrow. You can have animal activity on both the upstream and the downstream sides, as well as in the crest of the dam. And in some cases, this animal activity can be very aggressive. Here, for example, he found an animal burrow, and he's putting his camera in there and taking a picture. Let's see what it looks like inside. Well, it's a den, and you can see it's a tunnel going all the way through. So this can be very serious, because during a flood event, when you want the dam to hold back the water, if it's full of holes, you can have a concentrated seepage path that was created by the animal burrows. Muskrats are pretty sneaky. They will work underneath the reservoir and create their entrance under the water and then build their den upstream. Beavers will do the same thing, and you may not see the entrance, but you will see the activity, the sticks and stuff in the reservoir. Meanwhile, groundhogs prefer working from the downstream side of the dam, and they will tunnel in and build multiple dens, entrances, and exits, and things like that. So if you have a combination of the two, you can have a real problem. So here we have all of the groundhog activity, then we have a little bit of muskrat activity. All that's left is a little gap. And during a flood event, if that was to break through, we can have a real problem. Here's a video showing exactly that. This is a 90-year-old dam. And as they were experiencing this record flood event, they were actually observing burrowing animals exiting the dam at different locations. And you can see here is where there was a concentrated flow. As the reservoir came up near the crest of the dam, the flow broke through. We had a concentrated seep, and that eventually led to a complete breaching of the dam. Here's an example. Now, this is not a dam, but this was a canal or a levee system. And they traced the failure because of rodent burrows. So during the flood event, these burrows formed seepage paths, and it resulted in an estimated damage of over $50 million. So this could be a serious problem. What the Bureau of Reclamation did here was kind of interesting. They injected, as they wanted to know how bad this was, so they went to different parts of the embankment where there was a lot of rodent activity, and they injected in an expanding foam, and then they went in and did an excavation to see how extensive the network was. And here's a picture from that. Here's another picture just showing how they had tunnels and cross tunnels. And this is my favorite picture. They took the foam and they put an orange dye in the foam, and then they injected it. And then they went back and did a forensic, and you can see how connected these tunneling were. This is a pretty wide crest here. I'm guessing that's probably about 40 or 50 feet wide at the crest, but you can see how over time the burrowing animals pretty much turned this embankment into Swiss cheese. Another concern problem that related to seepage and embankments is the uncontrolled vegetation. In this case, it's at the toe of the dam. And you can say, well, why would that be a problem? Here we're doing a great job mowing the downstream slope, the crest, there's no vegetation, but at the toe of the dam, there's a problem. And the reason that can be a problem is if, remember, there could be a drain, and there should be a drain located at the toe of the dam. So if you do a cross section of the dam here, and then you look at where all these trees are growing right up to the toe of the dam, there is a drain outlet built into here, and the purpose of that drain outlet is to collect the seepage and discharge it. Well, with all these tree roots growing here, if you don't maintain a safe buffer, that drain can be completely obstructed with tree roots, because the roots are looking for water, and they'll find the drain and the perforated pipe, and that can be completely clogged. And that can totally eliminate the benefits of the toe drain system. So it's really important when you're inspecting the dam to make sure that that is not occurring. Looking at what tree roots can do, there are examples of certain types of trees like cottonwood trees where these tree roots are so aggressive that they will travel a distance of over 100 feet. So maybe that 20-foot barrier at the toe of a dam is not enough. It all depends upon what kinds of vegetation and trees you have growing around your dam. And other types of trees, some of them have very invasive roots on the surface. Others can have very deep tap roots. Here's one where the tap root goes down about 12 feet. So just going back to uncontrolled seepage, the big solution there is to have a chimney drain and a filter dam and a filter diaphragm, especially around the conduit. If you have that feature, I'm not aware of any dam that has ever failed because of uncontrolled seepage that had that modern defensive measure. If you have a chimney drain with a blanket drain and a filter diaphragm around the conduit, chances are you will never have to worry about that. Another thing to look at when you're inspecting the dam is look for differences in the vegetation. Here it's clear that something is going on. We have a lot greener vegetation right in this zone. And here's another picture. In this case, the person that was mowing the downstream slope, when they got to this zone, they mowed around it because it was so wet and soggy that it was hazardous to mow. So essentially what they did is they mapped out the seepage zone within this particular embankment. And as you're inspecting it, you're looking for any areas where you could have a high phreatic level that's daylighting through the downstream slope of the dam. And that could happen if you don't have good internal seepage collection and filtering. It could also happen if there's a defect in your filtering system. This particular dam was modified in the 1980s, and they used a geotextile instead of a sand filter. And it worked for a while, but eventually that geotextile became clogged, and then it just became ineffective. And if you had any kind of seepage coming from the dam where it's muddy seepage, that is a serious condition. It means the embankment is being eroded, and it needs to be probably the reservoir should be lowered and the dam repaired. Also, when you're inspecting the embankment, you need to inspect beyond the embankment. Here we're looking at the toe, and because of confined layers or concentrated seeps, we talked about that a little bit, looking at the dam basics, it's possible to get a concentrated seep at the toe of the dam and get what is called a boil. So here it looks like the water is actually boiling, and that is where the hydraulic gradient, there's a breakthrough through that confined layer, and you can see that the material that's being deposited on the surface is a sandy type material, and it's really forming a sand boil, and is different than the material that's around in the stream. And that's an indication of seepage going underneath the embankment. Other evidence might, if that was allowed to persist, you'd start getting something that could look like this, sand boils on the toe of the dam. And then we'll move on to the last major reason for dam incidents and talk about what to look at to identify the potential for spillway erosion and breaching. So here's an example of an NRCS dam in Mississippi, and the embankment appeared to perform satisfactorily, but obviously there was a problem with the auxiliary spillway. So what are things that could happen to a spillway in terms of maybe deferred maintenance? Sometimes it may be a result of the original design, that the engineers underestimated the erosion resistance of the grass lining for this particular case, and that you can end up with erosion starting at the downstream end of the spillway, and then it begins to head cut upstream and then eventually breach the spillway. And that's what we're seeing here in this series of pictures. And in this case, the erosion at this point, we have a vertical face of over 40 feet. So it started at the downstream end and now it's progressing upstream. What are some reasons why this might happen? Well, don't underestimate the importance and the value of the grass lining. If that grass lining really is the first line of defense and provides the erosion resistance or an armored layer over the spillway. And I really like this picture because it shows how something as simple as ATV, all-terrain vehicle activity, how that can impact the performance of the spillway. So here you can see the tracks coming around, going over the crest and also down. And we have very little flow going over the spillway. It looks like the crest of the spillway is worn down a little bit. We have a little bit of concentrated flow from the ATV tracks, and look at the amount of damage that's creating right here. Just that little bit of concentration. So you know that as the flow goes over the spillway, it's going to start to head cut and be damaged there. Here's an example of a road, a farm road that was built through the spillway. And these were bare tire tracks going through here. And that's the only location where the spillway eroded, was directly along the path of the tire tracks where there was no grass cover and it was just exposed. So again, how important that grass cover is. This is a great video from the Dr. Sherry Hunt and the Agricultural Research Service. They looked at just removing a strip of grass to replicate a tire track, and they did a series of studies of flow over the grass lining with that one defect to see how that affected the rate of erosion. And as you can see in this time-lapse photography, that it's only where that bare earth or the tire track was simulated, that's what initiated the failure. Had that feature not been there, this spillway would have performed satisfactorily and would not have breached. The next slide I'm going to show you is the exact same video, but very quickly, so you'll be able to see it more effectively. So that grass lining is very important for a spillway. Also, not just tire tracks, but even something as simple as allowing woody vegetation to grow in the spillway. So if you stop mowing it and you allow a different kind of vegetation to take over, that will cause flow concentrations and can result in initiation of erosion in the spillway and premature failure of the spillway. So here we have the spillway and it's flowing, and you can see the woody vegetation that was allowed to grow, and you can just see the difference in the flow. And if you go back to that first example I showed you of the dam in Tennessee, you saw how uniform the spillway flow was. As soon as you start getting anomalies in flow concentrations like this, this can result in erosion of the spillway. Now this spillway looks pretty good. It has a good grass cover. It still has the problem with these tire tracks. I imagine if that was to initiate, that's where it would erode first. But this spillway has a different problem. As you go down to the downstream end of the spillway, where it transitions into the valley bottom, let's see what's going on there. And in this case, it looks like the farmer excavated a access road. And so what's going to happen here is a flow that's going over the 2% grade all of a sudden now drops almost vertically, and there's no transition anymore to the valley bottom. Well, what would that look like if that flow was going through the spillway? So let's imagine a 100-year plus flow, and it would look like this. And so this is a whole lot different. The flow that's going through here, this is what the spillway was designed for, this type of flow. But at the downstream end, we have a lot of energy being dissipated. And we're essentially going from an armored slope to a head cut that's pre-existing because of the cut in the road. So if we were doing an analysis of this using the SITE software, which was developed by the NRCS to evaluate this type of spillway, we're essentially starting with the failure advanced at this location, and it's just a matter of head cutting upstream. So look for those kinds of modifications, inadvertent modifications to a spillway. And in the last just a couple of minutes, I want to wrap up with some other things that you might need to look for. If you have a very steep slope, or if it's saturated, you could have a slide or a slough, and that's what that would look like. Or cracking and slumping along the downstream slope. Or bulging. In this case, there's no crack, but it's bulging, and that was an early symptom of a slope that eventually did fail. So any movement in the slope, ultimately it can get very serious, like here, and it will progress until the embankment's breached. Gate failures. When you operate a gate, it should be well maintained. You can see this gentleman, he's using one arm, the gate is moving freely, and he's able to raise it and lower it. You should never have to use more than about 40 pounds of effort to raise or lower a gate. If you have to use more effort than that, like what these guys are doing here, we got 3 big boys with pipe extensions on there. These operators, stems, and gates are not designed for this kind of force, and you will break the gate. It's pretty much a guarantee. And one of 3 things will happen. You'll either break the stem guide and the stem, and it will you'll see it'll fail, like what you see in this picture here. It will break the stem operator. It could either, in this case, it broke it right here at the bonnet, right at the top, and snapped it off. In this case, it failed at the bottom of the operator, right there. And the worst case of all would be if you actually broke it at the gate disc itself, if it's separated from the opening, because this could be under 50 feet of water. And how would you ever be able to repair it or deal with an emergency like this? That would be very serious. So the rule is maintain those gates per manufacturer's instructions. They need to be lubricated, they need to be exercised, and never apply more force than needed than one person, like a 40-pound force, to operate the gates. So Ray, that's the content for this 90-minute presentation, and I would welcome any questions.
Outstanding, Paul. Let's let you give just a little bit of time here to go and get that drink of water and whatnot. My goodness sakes, you've given us so much information in a short period of time. If I remember correctly, you said that this was a program that you did over 3 days. Is that correct?
Yeah, we really have to thank Mark Locke and Steve Durgan. Those are 2 names that many people with the NRCS know, because they were both the chief national dam engineers for the programs. Mark Locke was responsible for starting the seminar 3 years ago. He said, Paul, I need to have a course developed now that our dams are reaching their 50-year life for NRCS engineers and other professionals that operate and maintain these dams to be able to go back and effectively inspect and evaluate dams. So we worked together to develop a 3-day seminar, and I just pulled some of the most important information from that seminar to share with us today. And Steve Durgan took over later as the National Dam Safety Engineer, and continued to help develop that seminar. To date, that seminar has been offered more than 20 times across the United States, and we've reached more than 1,000 participants.
Oh, that's excellent. Now I'm going to load up the questions, folks. You start throwing in the questions to Paul. This is your opportunity to really get some more detail if you want some more detail. The first question is going to go to Dan Siebert, though, and Dan's waiting anxiously to answer this one question while Paul gets a drink and of water and relaxes just a little bit, and then we'll start firing some questions at him. Enter your questions on the questions dashboard. Go to the orange arrow at the top right-hand corner of your machine. Tap that orange arrow, go down to questions, type in your question at that point and hit send. And that question will come into us. We got a few questions coming in. So Dan, the first question comes to you though, and that's on the PDH certification credits. Some clarity around what would be available through the National Watershed Coalition regarding PDH credits. So Dan, you still with us?
Yes, sir. PDH, well, first, obviously, the information presented today is at a level that it would qualify for those credits. The way you get that done is you need to request from me, not Ray, at nwchdqtrs@sbcglobal.net. You need to request credits. At that point in time, we will check the webinar records for your participation. Believe it or not, we can tell A, if you were present, and B, how long you were engaged with the program. And based on what that tells us, we will issue you an email which documents your participation. And as I said earlier, the webinar will be posted, so if the powers that be should question the content of the webinar in terms of its qualifying for those credits, you will be able to direct them to the website to view that information. So credits are available upon email request and confirmation of your participation and the length of your participation.
Thanks, Dan. Very, very important and seemed timely to what Paul was talking about too, the 3-day event squeezed down to the 90-minute presentation and now the questions period. And so we welcome your questions. So I'm going to start, Paul, and first of all, let's check in with you. Were you able to get a cool drink of something or a hot drink of something to take care of those vocal cords?
Yeah, Ray, I'm fully hydrated and ready to go.
Okay, so here's our first question. Mary asks if the tree is larger, is it better to leave that tree, better to leave it in place or remove it? What do you think?
Yeah,
That tree.
well, that's a slippery, Ray, that's a little bit of a slippery slope.
Yeah.
And trees do not belong on dams or levees. They just do not belong there for obvious reasons. But once they're there, you really have two choices. One is to remove the tree, and if it's a large tree, we're talking about removing the whole root system as well. So that is almost a dam rehabilitation project by itself. You can't just cut it off and walk away because you're leaving the most a critical part in the embankment. But you can play the long game or the short game. It depends upon how the owner, I would say how proactive the owner is. In some cases, and these are rare, and it'd be a very rare exception that you would do this, is you would allow the tree to remain, and as it's showing signs of reaching the end of its life, then you would have to take it out, but I absolutely never replace it. But my pat answer is no, you need to remove all the vegetation. Because what happens if, even if it is a big healthy tree, what happens if there's a great, a gust of wind and the ground's saturated and it just, it depends where, especially if it's at the toe of the dam or at the crest of the dam, and it takes a big clump of dirt with it. I mean, that's a serious problem at an embankment dam. So my advice is to remove it.
Yeah. And that becomes a restoration project at that point, right?
Yeah, it's the cost of deferred maintenance. It's so much more economical
Mhm.
to maintain the dam regularly than to wait and only do it after long periods of time. The other problem with allowing, I imagine if there's a big tree growing on it, there's other vegetation growing on it, and it promotes animal activity as well, because they'll start burrowing around the roots and making their homes in it. The tree will shade the grass won't grow, you'll have bare spots. You know, there's other things that happen as well.
Yeah. Our next question came in from Howard, and he's wondering how much the increased frequency of overtopping is due to upstream changes in the watershed. Any idea how much that affects the overtopping number compared to age of the dam, the inadequate maintenance, and et cetera? So changes in the watershed affect on overtopping.
Well, changes in the watershed can. Sometimes it's a plus, sometimes it's a minus. Um, for example, if it was before it was agricultural and it reverts back to forest, that would be a bonus. That would there would be less runoff. The more in a natural state the watershed is, the less runoff there is. On the other hand, if there's urbanization in the reservoir, you will get higher runoff. My experience has been, especially if you're doing a dam assessment and you do the hydrologic analysis, you do it for existing conditions, but you also do it for future conditions with full build out. And in most cases, that might change the inflow a couple percent. I think the more critical factor is what's going on downstream, especially if you have a low or significant hazard dam. Because in those cases, a low hazard dam is often only designed to pass the 100-year flood, and then the significant hazard dam may be designed to pass a fraction of the probable maximum flood. And as soon as there's development downstream, and if it can be shown that if the dam fails, it has the potential to create loss of life, then immediately it becomes a high hazard dam. So that's called hazard creep. And in that case, automatically the spillway would not have enough capacity and the dam would have to be upgraded to pass that. But that was a good question. There are a lot of factors that can affect overtopping, and one of them that I did not mention, and I'm glad that question was asked, because changes in the upstream watershed can also affect the frequency of overtopping.
Mhm. Thanks so much. How would you approach, Paul, modifications made by landowners to the principal spillway in order to fill their desire to hold back more permanent water? So, boy, landowners going in and making their own changes and that sort of thing, and hold back more water.
Well,
Your thought?
you understand why they would want to do that. In some places, water is gold, and it's just a shame, you know, to watch it come in and go out. But by doing that, they really are changing the design, because part of that storage may be reserved for flood protection. And if they start using some of that and not coordinate with the original designer, they're really changing the function of the dam. The other thing, any modification like that really should be done. I think these structures are permitted, and every state has a dam safety office, and it would be a violation to make that kind of a modification without getting them involved. And they're really there to help dam owners as well as to look after the interests of the public that live downstream of the dam. And they're an excellent resource. So I would caution anybody from making any modification to a dam without getting approval. A lot of modifications are often done with good intentions, but they have consequences that are not anticipated and can create a real problem. You know, a good example was the farmer that built that ramp to get up over the dam and get to his fields, not realizing that he reduced the spillway capacity. You know, there's an example in Hawaii at Kaloko Dam where the dam owner filled in the entire spillway, not realizing it was a spillway. And they had a flood event, it overtopped the dam, and 8 people died as a result. So some of these modifications can have dire consequences.
Thanks so much for
Hey,
that.
Ray.
Yes, sir.
Ray, this This is Dan.
Yeah, Dan.
I would also suggest that folks go back and look at the recorded webinar on easements, because there is some information there that's pertinent to that question in terms of easement defense and what what grounds a sponsor has to enforce the easement. And not only might that be a dam safety violation, it also may be an easement violation as well. So I would refer you back to the recording of the previous webinar on easement basics.
Sure. And that's
Hey,
on the National Watershed Coalition website that will show that website again a couple of times, address.
hey, Ray, just as a follow-up to that question, it is not uncommon to raise the normal pool of NRCS watershed type dams just to reallocate some of that storage, but it just has to be done, you know, it has to get permitted, designed, and it has to kind of be official.
Yeah. And for risk management for that landowner and the sponsors, right? Oh my
Yeah,
gosh.
exactly.
You're going to want to talk with some folks that can sign off on such things. Oh, very good. Thanks, Paul. Thanks, Dan. A good catch there on the, our easement webinar that we had and some of the things there. Rita gives us our next question. Our most common problem is the deterioration of the tow drain outlet pipes. What do you recommend to repair these tow drain outlet pipes in that situation?
Yeah, there's a couple of things you can do. It depends upon how deeply they're buried in the embankment. In some cases, they're very deep, and it's not practical to excavate them and replace them because you end up removing essentially the entire embankment. So what you could do in a case like that would be to strip the downstream slope of the embankment, basically build a modern chimney drain and tow drain and flatten the embankment and put in a new tow drain system. That could be one option, and abandon the other one. But if possible, and I would say in most cases that tow drain system is fairly close to the toe of the embankment. And in most cases, what we end up doing is simply excavating it, removing it, and replacing it, or replacing it with another one downstream and abandoning the one that's in place.
Thanks, Paul. And thanks for the question. The next question is coming from Trey. Considering the life expectancy of corrugated metal pipes, how much greater is the risk of seepage and or failure for dams with a composite versus a steel or a concrete versus steel or concrete pipes? So
Yeah,
that's the MP versus steel versus concrete. Yeah.
There are all kinds of pipes out there. And the go-to pipe right now for the NRCS is a pre-stressed concrete cylinder pipe. So that's the gold standard, where you essentially have a steel pipe with a concrete inner lining, a mortar outer lining. It's wrapped with pre-stressed wire and then encased in concrete. And it has really nice gasketed joints, long joints that can move and articulate. And studies have shown that after 50 years of service, many of them are pretty much as good as the day they were put in. With corrugated metal pipe, we know that depending upon the soil conditions and the groundwater, that they can have a limited service life. One solution, if you're proactive, is you can go in and slip line a corrugated metal pipe and insert either a steel pipe or a high density polyethylene pipe, a smaller diameter pipe inside the corrugated metal pipe, and then grout around it with a cement grout. And that can extend the life of that pipe very effectively. There are other pipes out there too, but I think we're trying to answer the question for an existing dam, what do you do? And if once you have a pipe in the dam, usually the most economical solution is to slip line it if possible. Otherwise, you have to do a cut and cover replacement, which means removing the existing pipe and replacing it with a new pipe. Or in some cases, you could put in a siphon, but that would be for a relatively small dam. To replace the outlet works with the siphon.
Okay, very good. Next question then is easy. We'll put Dr. Siebert's contact information back up here in a bit, but please don't consider it to be the closing comments. We'll do that later. And we are pushing up against our 2-hour mark, and Paul is willing to stay on and answer questions, and you'll want to hear Dan's comments too at the end. So just to let you know, but I will put that back up for you. Now we're speaking about our corrugated metal pipe again. How is a rusted corrugated metal pipe typically repaired? And I think you just talked about that in a principal spillway corrugated
Yes.
metal. Anything to add to that,
Yeah.
Les?
If you have a corrugated metal pipe drain, there's very little you can do because the diameter is so small. Usually it's a 6 or 4 inch diameter pipe, and you really can't slip line it. So you're looking at a replacement for that.
Mm-hmm.
For a principal spillway outlet conduit, if it's not too far gone and you're proactive and you get it early enough, you can slip line it. But you are, and in some cases, you can actually slip line it and not lose any discharge capacity, because the corrugated metal pipe is a rough pipe. You have a lot of friction losses. And if you replace it with a smooth pipe, like a plastic pipe, in some cases, you don't even lose discharge capacity. And so as long as the host pipe, the corrugated metal pipe, has enough structural integrity that you can slip line it, that is the most common repair.
Mm-hmm. And
Now
is there kind of a threshold,
sorry.
Paul, of size there for what you would slip line and what you wouldn't, or is it a matter of size and the deterioration that's already there?
Yeah, most of the embankment dams that I'm involved in, the diameter of the pipe is usually 24 inches or greater, and those are well within the realm of slip lining. I think even an 18-inch diameter pipe, that's not my area of expertise. I can't give you an answer exactly how small a pipe you can slip line. There are some technologies out there that if the pipe is strong enough to support the earth load, you can slip line it with a very thin material. That's mainly to stop a leaking though, and you'd want to make sure that the pipe had enough strength. It's kind of like unrolling a sock. It's a thermoset type a liner that's often used. But I think for corrugated metal pipe, you'd be concerned about it corroding over time, not being able to support the load around it. So the pipe that you insert in and grout basically has to have enough strength to take over that function. And so I guess that's the answer. I think when you start getting to, my guess would be when you're getting to pipes less than 18 or 12 inches, they're probably not candidates for slip lining.
Thanks, Paul. Thought there might be a threshold there of some kind. Well, let's talk about some bacteria. Let's talk about ants. Let's talk about that sort of thing. Let's start with that first question from Kirsten. And they said that we've got a serious, what I've been told is iron bacteria stopping up our tow drains. We custom designed a tool to try to clean it, but wondered if you have any other ideas regarding iron bacteria.
Yeah, the best way to deal with iron bacteria, I believe, is to have a clean out. I imagine they're working from the downstream outlet and trying to clean it from that point and work their way from the downstream upstream. A modern drain system will have a clean out at the upstream end. So basically you can access the pipe from both ends. And what we're doing on a lot of existing dams, if the pipe is still in good condition, we'll excavate at the upstream end to uncover it, and then we'll have a sanitary sweep that essentially connects to the existing drain pipe, and then it sweeps up and out of the ground and has an access port that exits the ground surface. And that allows the maintenance staff to do two things. One is they can go in periodically and flush it, so that they basically inject water in the upstream end and then flush everything out the downstream end, let gravity do the work. And then they can follow up with a camera, and it can be either a push camera if it's a small diameter pipe, or a crawler camera if it's a larger diameter pipe, and then inspect the conduit. So that's the best way. In some cases, you can use conventional sewer cleaning equipment that will agitate. You basically thread it in the downstream end. It will agitate the iron precipitate, and make it more of a fluid and flush it out. And you did basically start from the downstream end and work your way upstream. I would caution that though, because that's a fairly aggressive method of cleaning a drain pipe. And if you were to encounter a part of the pipe that's so deteriorated that you have exposed earth, you'll actually cause damage to the dam.
Yeah, yeah. Could be asking for more problems than you were trying to resolve.
Yeah. Just as a side note, I wish I would have put a couple of slides in on this topic. Animal guards are very important as well on these drain pipes. There are cases where they've actually found a dead beaver 100 feet inside the tow drain pipe where they've crawled in, and other animals as well. So animal guards are important on the entrances of these drains.
Mm-hmm. So we're talking about things that be impacting our dams, and our next question comes from Shannon. And how serious is the ant activity, like fire ants, in terms of dams and concerns?
Yeah, there's a public safety or worker safety issue there. There are a number of hazards related to animals and insects. You know, ticks, mosquitoes, fire ants. As well as snakes and other things. But as far as ant damaging an embankment, I have seen some really nasty cases where it's just one mound after another, after another, after another. In most cases, it's superficial damage. It doesn't. I have not seen it go very deep, but that doesn't mean that there's an exception to the rule. That's just my experience.
Yeah, it'd take quite an ant hill to cause problems, but you've not necessarily seen that happen, Paul.
No, I would be concerned though if it was happening in the auxiliary spillway because it would affect the grass cover.
Okay.
And you know that's always, I can't emphasize that enough. These grassline spillways, they were designed to be well maintained, and it's all about maintaining that healthy grass cover.
Yeah. We're going to switch gears a bit. Question from Jeffrey: are dam designs going to change, engineering-wise, with the stronger storms that we are experiencing due to the climate change, or have some dams been changed because of stronger stream frequencies? So, question related to climate change, the increase in stronger storms that are occurring and pretty well documented. So, what are you seeing out there, Paul, in terms of dam design is going to change and in relation to climate change?
Well, maybe I could answer that question by just sharing my life experience. You know, I started working on dams in 1983, and the way we're mostly rehabilitating dams now. We're not building many new dams, although we still are building new dams. But when I started back in 1983, roller compacted concrete, articulated concrete block mats, HydroPlus fuse gates, all kinds of other technologies, plastic pipe. They weren't even available at that time. So engineers are coming up with all kinds of new materials and new ways to solve problems at aging dams. Some of the things we started off by looking at 5 dam failures, and in most of the cases, those dams were built early on, and they did not have the defensive measures that a modern dam would have. So we have a lot of catch-up work to do. Just something as simple as having a filter diaphragm around an outlet conduit. I don't know what the statistics are, but it wouldn't surprise me if most earth embankment dams do not have that defensive measure. And that means that they're all prone to potentially that failure mode until that defensive measure has been added to the dam. So there's a lot of dam rehabilitation work to bring existing dams up to current design standards. And I imagine these design standards will continue to change as we go forward.
You know, related to that, and this is a question related to the changes in the state dam in, you know, requirements in states. And I know you can't go over all 50 states and the island territories, but have there been significant changes in the laws and the requirements? And so we go in and we do one restoration project. Does it require several others to bring the dam up to code then, or up to current standard? Or
Oh yeah, every state is
Mhm.
its own, has its own authority. And
Mhm.
we do have national standards. And the purpose of the national standards is to help the states be more consistent. But
Mhm.
even with those national standards, they're not essentially required. So
Mhm.
every state has different ways to classify dams, different standards with respect to spillway design, discharge requirements, and other features as well. Some dam safety programs are very mature and robust. Others are, still developing. So
Mhm.
that's the thing. But one of the good news is that the Natural Resources Conservation Service has a very mature dam safety program, and
Okay.
they have a National Engineering Handbook, and their standards are well established.
Mhm.
So they should be consistent for all the watershed dams. I believe that there is a lot of consistency.
And if I remember correctly, the NRCS standards and specifications also take into account the state standard. So if you're in Oklahoma or Texas or someplace, and the NRCS standards are brought up to that state standard if there is a difference. Is that
Well,
correct?
it's usually the other way around. It's
Okay.
I think the NRCS standards in most cases
Mhm.
are more conservative than the state standards, and it's more the state standards catching up to the NRCS standards. That's been my
Ah,
experience.
very good. Very good. Okay. Yeah. And let's see. We've got the next question coming in from Susan. Is there a similar problem with sediment basins where people want to gate outlets to increase the retention time?
Yeah, I think there's always a temptation to want to improve the performance of structures. Um,
Mm,
well, one of the things that's emerging that's becoming extremely important, especially with these detention ponds and things like that, is a public interaction around these sites. A
mhm,
lot of detention ponds are in urban areas,
mhm,
and we have to be really careful. We have children playing in these areas and things like that, and sometimes these modifications that we make can have consequences as far as public safety goes as well. So I think I might sound like a broken record. If you're going to make a change to a facility, you really have to start with the original designer or the design intent. And if it's a permitted structure, you have to get a permit to change it. So I would be careful. But there's nothing wrong with evaluating an existing structure and assessing whether or not it should be changed to improve its performance or to improve its value. There's nothing wrong with that.
mhm, mhm. Yeah, but just with caution, risk management is so important nowadays, isn't it? We want to
Yes.
measure back our risk and get a hold of the professionals and make sure that the permits are done and the professionals are looking things over with you. And so that if something did go wrong, you didn't lay your own personal finances out there, especially for the landowner and the sponsors. Now let's do talk about this. For those that have been asking for the email address, it's posted up on the screen again for the PDH certification. Thank you for that question. This person, Jana or Jana, has offered to us, when sites are over 50 years old, how would a soil and water conservation district go about giving them back to the landowners to eliminate the expense of operation, maintenance, inspections, and cost to the partners? Would specifically be thinking of grass waterways and small structures like this in a watershed area, not necessarily dams. So this is a transfer of that to sponsorship or operation and maintenance inspections and that sort of thing. Is that even possible? And if so, how would a soil and water conservation district, watershed district, any other sponsor be able to do that?
Well,
Any,
for any dam owner, if they no longer want to operate or maintain the dam, they don't want that responsibility,
Mhm,
um, they always have the option to sell it or to transfer it to someone else. They have
mhm,
another option too, and that is they could always decommission it, breach it.
mhm, mhm,
And usually when you're looking at a project, it starts with the planning study, and you look at the value it provides For example, if it provides flood protection downstream, you weigh that value against the cost of rehabilitating it or maintaining it. And if the benefit cost ratio isn't there, or if there's no one willing to maintain it, then breaching is a perfectly, acceptable option. The one caution though is if you decommission a project, chances are you will not get it back. So you better be very careful. It's a one-way street. It's very unlikely that you'll be able to build it. So a lot of these projects have tremendous value just by the fact that they exist. And if you wanted to build another dam with a recreation reservoir or whatever, chances are the permitting environment won't allow you to do that anymore.
Yeah. I'm kind of sensing a theme here too, that, if you're a sponsor, if you're a conservation district sponsor or a city or a county or a watershed district or irrigation district, whatever it might be, oh my gosh, the importance for a board, especially new board members, to get acquainted with what risk is out there to their organization is always important, isn't it? And
Oh,
to
absolutely.
yeah, which dams are operating in their particular area. And we think, I'm housed in the Pacific Northwest, and I think, there's not many of them up here in Washington State. Oh, contraire. There are several dams there, and you'd be surprised who the sponsor is and who's holding the risk management bag, you might say, of concern, and making sure that you know that as a governing board.
Yeah, just a comment on that. I have been involved in responding to multiple dam emergencies. And once you're in that mode where you're looking at a dam that's susceptible to failing, or that is failing or has failed, it's the cost of litigation and dealing with the consequences are orders of magnitude greater than the cost of if you would have just rehabilitated the dam. And I understand that money is tight, and for most dam owners, if you're looking at $1 million rehabilitation, it's just so difficult to find the funding to do that. But the cost of having a dam incident or a dam failure, again, it's orders of magnitude greater than that, and you don't want to be there. So I like what you said, Ray, about managing risk. The people, the decision makers, they really do need to understand what risk they're dealing with. And if they can't afford to rehabilitate the dam, then the decommissioning option is often the best option.
That's good. I'm going to let you get another drink while Dan and Lisa may want to weigh in on that last item. Risk management, governing boards, sponsors of projects, staying on top of things. Dan and Lisa, some of your thoughts. This is a road both of you have been down a time or two.
I would say that if you have something like that in mind, you need to proceed with caution, because it appears pretty simple on the front end, but there is a significant cost, either or both legal costs as well as some engineering expense to decommission or removal. Also, there are some regulatory folks involved that may not agree with your decision to divest yourself of responsibility. And I would say that even though many times I hear people claim immunity from being sued or legal authority because of their government status, I can tell you that that you can sue the government. You can actually sue the federal government, and if you have an upstream flood control structure, there are tons of correspondence, plans, engineering plans, designs, and so on and so forth that have both the Soil Conservation Service / Natural Resource Conservation Services stamp on them, as well as legally binding documents in place that place a sponsor in what is viewed by the regulatory community as an ownership role. at a personal level, I would tell you that I don't ascribe to the point of view that that sponsors own an upstream flood control site unless they purchase the property on which it sits. They're easement holders, but that's not the way, I would tell you, that's not the way the regulatory community views it.
Mm-hmm.
But anyway, not as simple as it seems. These projects are built with structures in a series that how one functions may affect how others function downstream. And there's a lot of things to navigate in a decommissioning or a transfer of responsibility. And if you want to explore that further, if you'll shoot me an email or shoot me an email with your phone number, I'd be glad to chat with you on the phone. But it's a fairly complicated thing, and not one that's filled with success, joy, and a nice cake at the board meeting because you were successful in transferring the responsibility to someone else.
Yeah, I know trees are easier to hug than dams, but you kind of want to go out and hug your dam and make sure that it's operating properly and maintaining, and people know who it is that's responsible for the operation and maintenance and the sponsorship and so forth. So this is a good question for Paul and you, Dan, and that's and Lisa. Are there resources, fact sheet, part of the handbook for informing the sponsors or compiling the information to be able to inform sponsors about risk management for dams? So, you know, I'm a brand new board member of this group that is a sponsor for several dams in my area. What do we got for resources? Fact sheets, etc. Anything like that?
Well, Paul, trying to answer that question, I think your number one resource is the Natural Resources Conservation Service and their local office.
Mm-hmm.
I would start with them and pay them a visit, and especially if you're new to dam ownership and want to be educated. I think I'd sit down and talk with the state engineer and say, you know, could you help me, because that's part of their function. It's a key part of their function, I believe.
Yeah, yeah. And they would know where the dams are located and the locality and that sort of thing. Lisa, go ahead, please.
Yeah, Ray, I would highly recommend folks use the National Watershed Coalition as a resource as well. They have many fact sheets on what sponsor responsibilities are, and have done several workshops on that. So I think one of your best as a board and as a sponsor, having that relationship and communication open with each of your landowners is very, very important, so that if you have issues and problems, those folks are going to know it before you do, and they need to have a one-on-one relationship with folks that are sponsors.
Yeah, that's very good, Lisa. And then also, it's timely, right? That I've got the Dan's note up here, both his email address and the website where you could go find those resources at the National Watershed Coalition website. So, so that's important.
There are some things there on the website, Ray, that are downloadable that speak directly to that question.
And then, you know, just an observer, your moderator for today, I just can't help but think that $25 is a pretty good investment against 155 million per one fiscal year, and PL 566 and also our dam rehabilitation. But you just mentioned another compelling reason to get on the board with the National Watershed Coalition as a member and enjoy those resources that are available. So thanks for that. All right, we're going to go back to ants for just a little bit, and it looks like we're winding up with our questions. So do you, Paul, do you have any experience with red ant damage? Not the fire ants, but the red ants. They typically don't have a mound, but we have seen them denude an area of up to 8-foot diameter around the entrance. Do you know how deep and extensive the tunnels of a red ant might go, typically?
I thought I've seen everything, but what was just described, I have not seen. I sure would like whoever made that comment to send me some pictures, and I'm going to look into it. There is a federal manual on it's titled Animal Impacts to Dams, and I believe it does include fire ants as well in there. And I don't have the time to look it up right now, but I'll try to answer that question by email. It's something I need to do a little bit of research on.
Okay. So let me just pop that back up on the screen, and Karen will invite you to shoot a note to Paul, and he would like to do a little bit of research with you on that. Copy Dan, of course, would be good. And so, Paul, oftentimes we get in our vehicles, we go down the road a little ways, and we say, dang, I wish I would have said that to that group. And you still have 180 some folks on the line here. So we're going to give you the first cut at this, and then we're going to turn to Dan for some closing comments. But you get the first charge at, geez, I wish I would have said this to the group. Any of those thoughts that you got?
Well, I just want to thank everybody for taking time out of their day to educate themselves on this important topic. I'm assuming that many of you are responsible for operating and maintaining dams or making decisions about your dams. And it's an awesome responsibility. You know, a lot of people are counting on you to do a good job because the consequences, especially for the high hazard dams, are, you know, people live downstream. And so thank you for taking the time. I hope you learned something, and you have a very important job to do. And I hope this helps you do your job better.
Paul, I can hear the applause going on out there among the folks that joined us today. At a high water mark, we had over 250 folks that you were able to reach with your remarks. And I know Dan and Lisa have some things to say too. Lisa, let's go to you first, and then we'll close with Dan.
All right, thank you, Ray, and thank everyone for sticking with us for our second in this series of webinars, and I hope that you found the information useful. Paul, we can't thank you enough for taking time out of your day to make this presentation and to give these folks some things to really be thinking about. Inspections, there's nothing that is better than having boots on the ground on those sites, keeping an eye on them, not only during high rainfall events, but even during times when everything seems somewhat normal. So be vigilant and keep your sponsors informed and keep your landowners informed. So once again, if you enjoyed this webinar or others that you've listened to from the National Watershed Coalition, please consider becoming a member and like us on Facebook. Thank you.
Thanks, Lisa, and to Dan for our closing comments. And right before we go to you, Dan, want to just say thanks to the presenters and the sponsor. We also have, like I say, we went a little bit over time today with purpose to answer those questions and to squeeze in 3 days worth of seminar into just 90 minutes. So Dan, take us to the finish line, please.
Ray, I would just echo the comments of thank you and expressing our appreciation to Paul for his good work and to you for your logistical work. Excellent webinar. Appreciate everybody hanging in today. I'm already getting some emails for folks looking for PDH credits, and we'll address those. It's important to remember that inspection forms the basis for many functions that sponsors have. It helps you prioritize your operation and maintenance. It helps you prioritize sometimes scarce resources to make sure that you're addressing the most important things that you need to. It's obviously very important in the world of dam safety, and we feel it's just something that you can't know too much. Inspection is protection. Appreciate everybody spending time with us today. As Lisa noted, there is a great deal of resource material on the website, as well as membership information. And with that, everybody have a great day.
Thanks so much, Dan. There was one final note in here, the Facebook name. What would be the Facebook name for the folks that are listening?
You can look on Facebook for National Watershed Coalition, and it'll take you right to our page.
Excellent. Excellent. Dan, Lisa, Paul, thanks so much. Let's close today's webinar. And if you do have questions, don't forget to make note of that and send those to Dan there with the information listed. Take care, folks. Be well.
Thanks, Ray.
You bet. My pleasure.